that's making star clusters.
Yeah, thanks very much. It's, again, a great pleasure to be here in Santa Cruz, especially to talk about Star Cluster Factory, a project I'm doing with Oscar Gertz and Mark Gilles at the University of Surrey, not so far from London in the UK. So what is behind Star Cluster Factory is trying to understand, getting closer to understand how stars form, in particular star clusters formation, globular cluster formation, and how these systems evolve to what we observe in present-day Milky Way. So very quickly, what you have to start with is very high-density initial conditions to form stars. It's a long and difficult process when you form your star clusters. It takes time and a lot of efforts. And at some point, unfortunately, you get some perturbation, and then your cluster is in big trouble. And you lose mass. So in this context, how to probe galaxy evolution? The fact is, basically, we have pretty well-known initial conditions from the CMB. We have good clues about the end products, what we can observe in the local universe, for example. But in between, we are struggling with the poorly known physics of star formation, of feedbacks, of all the hydrodynamics that takes place. And the point is that if you are interested in stellar objects, you have a view of stellar objects. If you look at the size, magnitude, or luminosity, here I give some example of masses. Up there you have a zoo of objects starting with the giant ellipticals up there. If you go to smaller sizes, smaller masses, then you enter the realm of compact ellipticals. Some of them are smaller than that, so let's call them dwarf elliptical. Some of them are even more compact. So what is more compact than compact? It's ultra-compact dwarfs. At some point, you start going in the domain of globular clusters, but turned out some of them are extended. And if you close the loop, then you will find the dwarf ellipticals. So basically, it's a big mess, but maybe there is some kind of a gap or lower density in this area up there. But guess what? This region is slowly but regularly filled by the new detections of more and more objects up there. So what I want to tell you with that is that there is a not clear separation between galaxies and star clusters. It's actually quite difficult to define what a cluster is compared to a galaxy. And we don't really have a clear separation between the two families. So it's probably a sign that we can learn about one from the other. We can learn about galaxies studying star clusters, and we can learn about star clusters studying galaxies. So that's what we are trying to do with the Star Cluster Factory. Because we know that star clusters actually probe their environment, where they probe the physics of the interstellar medium. When they form, we can have a look at embedded clusters, so young objects still shrouded or embedded in gas. We could also go to more extreme environments and see the formation of young massive clusters, these huge beasts, for example, in intended galaxies. More than 10 to the 6 solar masses, that's really huge stellar clusters. And we can also use them to probe the physical condition of the formation in the early universe, where the globular clusters form, so it's something like 10 gigayears and even more ago. And when you do that, you realize, and Jean said that already earlier this week, that there is bimodality in the globular cluster population. So if you plot here the histogram of colors for the globular cluster, so for example in M87 here, but it's also valid for other galaxies, you find that you have two subpopulations. The first one is blue. Blue clusters are so-called halo clusters. They're metal poor, and they don't show any sign of rotation as a population. They're especially extended around galaxies. The other population is the red cluster. So they're called disk, maybe more bulge clusters. They're metal rich. They do rotate as a population, and they're more specially concentrated in galaxies. So there have been several propositions, several scenarios to explain this bimodality, this formation. How do you get this type of populations? It has been proposed, for example, that some clusters form in the progenitor, so the blue population will form in the progenitor, and then this progenitor will actually merge in gas-rich mergers, creating the red population. There is also the population by Duncan and Jean and Carl about the multi-phase collapse, formation in different steps for the two populations. And yet another scenario where the blue cluster has been accreted on the galaxy and the red one formed in situ. So to try to understand these processes, to try to see the link between galaxies and star clusters, we can actually use present-day globular clusters to probe the past steps in galactic evolution. So we're talking, of course, about the formation and the early evolution of the clusters. Formation in mini-halos, for example, at very high redshift through thermal instabilities. At high redshift galaxies through gas-rich mergers, again, in over-pressurized environments, through tidal or turbulence compression, for example. You have to get extreme conditions to get all this mass of gas to convert into 10 to the 6, 10 to the 7 solar masses objects. And once you have passed this phase of formation and early evolution, then you have to look at the evolution of star clusters. Internal evolution through stellar evolution, every star evolving according to its mass, its solar type, etc. Relaxation, the interaction between the stars is very important. Evaporation of the cluster. And of course, you have to put the cluster in its environment. And, all this internal evolution can be stated in terms of the half-mass relaxation time, so that basically the path at which, the pace at which the cluster evolves, so it's the link between the mass and square root of density for the stars. And when you put your cluster in its environment, then you have to see how it responds to external perturbations. So basically, you have two kinds of perturbations. If the perturbation is short-lived compared to the relaxation time, it will be in the impulsive regime. If it lasts much longer, it will be in the adiabatic regime. So these type of perturbations, there are many of them that have been studied by many, many authors. I will just make a very quick list about that. There is a ton of literature. You can see the effect of tidal shocks with giant molecular clouds when the cluster passes by GMC. You can have a look at the effect of disk crossing, compressive shocks when the cluster goes through the disk, across the spiral arms next to a bar. You can see the effect of galaxy merger, the accretion into galaxies from a satellite, for example. The effect of orbital eccentricity, which is very important over the long-term scale for star clusters, the adiabatic growth of galaxies through cosmic time. And of course, you can combine all these and many other aspects, put all these things together and see the relative weight and how star clusters actually respond to the cosmological evolution of their hosts, in plural. So we'll just show you a very, just a handful of examples of this kind of study, starting with this paper we just published with Mark Gilles, which showed that basically tides are safely limited. So what does that mean? Let me create a star cluster. Here I plot the radius and the energy, and I choose one cluster model, so one potential basically, which has a gravitational potential, is a line of zero velocity. So now if I want to render this with particles, with stars, I can give the stars any kind of velocity I want between this zero velocity curve and an energy of 0. So let's do that. Let's take an example. So this is a star cluster following this potential. And now let's apply some tidal perturbation. Like any tidal perturbation, energy goes at the radius square. So this means that for every of my dots here, I had something like radius square, and I get that. So you see no much perturbation in the central part of the cluster, that's normal, and the outer part is highly perturbed. And then you see that in the outer part, these stars have gained enough energy to be above 0. So this means that they are not bound to the cluster anymore. In other words, the tidal effect, the tidal perturbation is stripping the cluster, and I can remove these stars. If I do that, I immediately notice that the cluster shrinks, has a smaller size. And if the cluster shrinks, it becomes more resistant to further tidal perturbations. So this very simple effect has actually been stated a long time ago by someone who had no idea about star clusters, saying that what doesn't kill you makes you stronger. That's exactly what it means. So if you apply this effect to repeated tidal perturbation, for example, repeated interaction with giant molecular clouds along the orbit of a star cluster in the galactic disk, then you can reach the conclusion that young clusters have a universal size. So what's happening there is that you have two competing effects. You have the internal evolution of the cluster, so the interaction between stars that makes some expansion. And this is competing with mass loss, so the perturbation, the external effect from the rest of the universe, basically, but of the galaxy, of the molecular cloud passing by. So how can we visualize that? If I plot the mass of the cluster as a function of the density, half mass density, but whatever, I basically have two regimes. If the cluster is very dense, the interaction between the stars are occurring a lot, many times, very often, so that dominates. So we are in the ray accession dominated regime where internal evolution is very important. But if the density is smaller, then we are more fragile, more sensitive to the external perturbation, in particular the encounter with giant molecular clouds. So now let's take a few examples with typical density for the Milky Way. So different cluster and see how they evolve. So for the blue dots, which lie in the ray accession dominated regime, what happens first is that interaction between stars make them expand. At some point, they reach the tidal boundaries, the Jacobi surface, if you want, and they will escape the cluster. They will be stripped by the tidal field. So this is the typical evolution that they have. If now I am in the GMC encounter regime, more sensitive to external perturbation, that's the exact opposite. I will first lose mass, and then I will shrink, and I will go toward further ray accession dominated regime, and the cluster would evolve like that. And you see that where you started, your cluster will go toward this attractor solution, radius, half mass radius proportional to the mass, to the 1/9. So very, very weak dependence of the size and the mass. And this is why when clusters form in environments like Milky Way, for example, they seem to have a universal radius, because whatever the mass they have, whatever the properties of molecular clouds you have, you will, because of this very weak dependence, you will always get the same radius. And this has been observed. This is fully compatible with the observation of young clusters by Søren Larsen, for example, who found a typical radius of 3 parsecs for clusters in the Milky Way. Now let's move to another regime, another type of perturbation, which is the effect of galaxy mergers. So what I'm showing here is two galaxies interacting, and I chose 2 orbits in the galaxy, one in yellow and one in red, if you can see them, and I put the exact same cluster on the 2 orbits, and I show them here. So there are few particles so that you can really see the differences, but that doesn't matter much. I skip all the technical details. It's actually 2 different simulations. I couple them with the use of tidal tensors, extra. You don't really care. But here you see you have the interaction, and if you have looked at the clusters, you don't really see anything happening. There is no direct effect of the collisions. The galaxies are merging now. You have a final coalescence, and what you can notice is that the 2 orbits are quite different. The red orbit has been ejected to the tidal tails, so weak tidal environment, while the yellow one is staying around the central part, around the merger remnant. And after a few 100 million years, 1 gigayear, you start to see the difference in the 2 clusters. You see that this one on top have lost much more mass than the other because it's in a strong tidal environment in the yellow orbit, while the other one is in the almost tidal-free environment. So there is no direct effect of the collision, but there is an indirect effect, changing the orbits after the long-term evolution of star clusters in galaxy mergers. Now the trick for us is to put these and other effects all together and study that in a more complete cosmological context. That's why we are doing this simulation of the formation of Milky Way. So it's a zoom-in simulation, same initial conditions as the latte simulation. We use the Ramsey's code, and we have the physics of star formation, winds, radiation pressure, supernova type 2 and type 1a, following Oscar's work. And you see the formation of the Milky Way through major merger, minor merger, accretion, etc., all the classical business. We run the simulation till 0.5 because I'm too impatient to wait till redshift 0. And then we are studying the properties of star clusters, the star particles that we actually form in this context. So what we have here is the evolution of the stellar mass as a function of look-back time. You have the redshift on the top. And on the bottom panel, I will show the in situ star mass fraction, so the fraction of stars that formed in the Milky Way, as opposed to stars that have been accreted later. And you see that, this kind of evolution. So you see that high redshift in the early universe, the growth of the Milky Way, as expected, as inferred from observation, is dominated by major mergers. Here you see actually the times of the merger-merger events. The last one is at redshift 2, more or less. And you see that every time that you have a major merger, you dilute your fraction of in-situ star formation. Of course, you bring more non-in-situ accreted stars, and this fraction drops. Until you reach the non-major merger phase, when the star formation is happening in-situ, and this fraction goes up to, I think, 95% at 0.5. So we have early growth via mergers, you have drops during the merger, and you have a late steady increase with a slow star formation, something like 1 to 10 solar masses per year. Using the simulation, we can track the different subpopulations, the in-situ and accreted cluster. You see them in-situ in red, accreted in blue. The dotted lines correspond to the old population, so that what would correspond to globular clusters only. And total is a full Milky Way, of course. So we have accreted clusters, and we can look at their properties. They are metal poor, minus 1.3. In observation, you get minus 1.5, so it's not so bad. They don't show any sign of rotation as a population. They are especially extended, as you can see on the plot. So they are just like the observed blue cluster, the observed blue population. The in-situ cluster are metal-rich, Fe over H over minus 0.8, so you would expect 0.5. It's not minus 0.5, it's not so bad either. They do show sign of rotation, and they are more spatially concentrated, as you can see here. So they are just like the observed red clusters. So these formation scenario that we had in the simulation support the bimodality scenario from Cote et al. In 98. But we can still go further and look at how these things evolve, and we can monitor the tidal history. So here again, I have look-back time, and the y-axis I have this complicated quantity, which basically is the strength of the tidal field. At very, very rough, at zero order, you would say that the strength of the tidal field, this quantity, goes at the mass divided by the radius square. That's only valid for point mass galaxy, but it will be okay for us for the moment. It just gives you an idea of what's happening. Basically, the tidal history can be divided into 5 phases. You start up there with compressive tides. It's basically helping the galaxy formation, also star cluster formation in the universe when there is no huge overdensities. So early compression at redshift above 5. This is then followed by the phase where the major merger dominates the growth of the Milky Way. So you increase both the mass and the radius through the transfer of angular momentum. Then you have the in-situ star formation kicking in, becoming more and more important. So here you keep more or less a constant size, but you increase the mass. And at some point, for some reason I don't fully understand yet, the increase in mass will take over the constant radius. So remember, you don't have the same power here, and you will get this rise here. Maybe it has to do with the formation of the disk, but I'm not quite sure for the moment. At the very late stages, redshift below 0.6, you will get a slower growth with just a weak star formation as we approach redshift 0. So if we look at that, basically before redshift 2, we have comparable tidal history for both populations in situ. So the red clusters are accreted, so the blue populations. But after that, because the in-situ clusters are more centrally concentrated, they live in a stronger tidal field. And this means that they will have completely different evolution. The critical point is that if you look at the value at the end, it's the maximum of this history. Meaning that in whatever cases, for the two populations, we had weaker tides in the past. In other words, if you use these present-day properties of your tidal field in Milky Way, the one you can observe, you highly overestimate the mass loss over the about time the cluster have lived. So the next step for us is to compute the actual response of a cluster evolution through dedicated direct and body simulations, through also mathematical models. So now I'm reaching my summary. I've told you that star clusters co-evolve with the host, and they can tell us how. We can study both together. Tides are self-limited. The cluster have a universal radius coming from the repeated interactions, repeated effects of giant molecular clouds in the early phase of their evolution. Galaxy interaction have no direct effect on the cluster evolution. Of course, they have an effect on the formation, but not so much on the evolution. But they shuffle the orbit and alter the long-term evolution. We had the bimodalities in the population retrieved. through in situ and accreted population. And basically, the title is stories follow the galaxy build-up phases. Thank you.
Questions? At the back.
Very nice, interesting work. I'm wondering about the blue globular clusters, which you call accreted. The problem when you call them spatially extended, but relative to sort of the halo or a satellite population, 10 kiloparsecs is not that far. People have had trouble in the past reproducing that fairly compact configuration by pure accretion. I'm wondering how you get around that.
I'm not really trying any parameter search to feed that. I'm just using this simulation. You know, it takes like 6 months to run, so I cannot really do a parameter search. What we have for the accreted population is like a little bit flattened spheroid. It's not really. It's comparable to a halo, but it's not very extended, as you said. So it's not a perfect match to the Milky Way, obviously. And the point is that I'm not comparing directly my data with star clusters because I only have tracers. I only have particles that I can say have formed as globular clusters, but I don't know how they evolved. For example, I expect that most of them will dissolve. And I don't obviously expect the same dissolution rate in the outer halo or in the central part of the galaxy. So that's why I haven't shown any numbers, any actual statistics in terms of number of clusters, because I don't know which one are dissolving or not yet. That's the second step.
That's sort of going to make the problem worse, I guess. But basically, what redshift are these things accreted at?
So most of them are created during a major merger event, so before redshift 2. Okay. You have some coming from minor mergers later, but that's not the majority. Okay. Most of it comes before redshift 2.
And that's really specific to the Milky Way merger history you've inferred, right?
So the Milky Way has a pretty well-defined age-metallicity relation for globular clusters, and previous simulations have struggled to reproduce that. Have you looked at that?
I'm looking at it right now. Okay. It's a matter of hours before I get the plot.
Can I ask another question? If I can ask another question, so you mentioned at the beginning, galaxies have dark matter halos. So do your star clusters form in mini dark matter halos, which are subsequently stripped?
Some of them at the very high redshift, yes. They do. Well, it's difficult. At some points, it's difficult to tell the difference between a star cluster and a galaxy at these very early stages. So what we have is just particles surrounded in dark matter halos that are accreted. And we can identify them either at small galaxies or big star clusters. So it's actually difficult to put the boundary here. But yeah, this situation happens, yes.
Okay, thank you.
Last question? Okay, as one of the 3 speakers, I'm sure that we would all appreciate another round of applause for the talks of this session.